Good morning. Am I audible? Anybody please confirm I'm audible.
Yes, sir, you
Yes,
are
sir.
audible.
Yeah, thank you. And the slides are changing to the next slide.
Yes, sir.
Yeah, thank you. We'll start on the next representation of finite state machines. We have already studied Mealy machines. We'll study the Moore machine today. So the entire our steps will be as follows again, similar to Mealy machine, is that first we'll have a problem description, and then we'll have an formal representation of the description as a Moore machine. Then we'll go ahead with the implementation of the formal representation using a circuit having flip-flop and gates. And then maybe we will see that it's possible to convert a Moore machine to a Mealy machine and vice versa. Okay, so let us start with the definition of Moore machine. It is another representation of a finite state machine with a slightly more simpler setting. So the simplicity is that the output depends only on the present state. It doesn't depend on the current input. So just as in Mealy machine, you can also represent this as a tuple consisting of capital Q, which is the set of states, an initial state Q naught, a sigma, which is the input alphabet, which is the all possible combination of inputs that might come in. Delta is all possible combination of outputs that might be generated. Small delta is a transition function which is given a state and an input gives the next state. So it is a mapping from Q cross sigma to Q itself. And then the change is in the last definition. The lambda is the output function. So lambda maps, or in the Mealy machine, lambda was mapping Q cross sigma, that is the state and an input to the next state, to the output. So the output depends on both the current state and the input. Here, output depends on only the current state. So lambda is the output function is a mapping only from Q, the set of states, to delta, the set of outputs. So this is the only difference with the Mealy machine. The state transition still is a function of both the current state and the input, but the output is a function of only the current state. Okay, so what does this mean? What does this mean? So we have seen two representation of a Mealy machine as well as for the Moore machine. One is a state transition diagram consisting of vertices and directed edges, and another is the same thing represented as in a tabular form, the state transition table. So if we look at the state transition diagram, you see in a Mealy machine what we had was we had a set of states P and Q here. We had a set of transitions from P to Q, and the transitions happened on inputs. So if you are in P, if you get an input of 1, you move to state Q. If you are in Q, you get an input of 0, you move to state P. So the transitions happens on input, that's fine. Transitions happen on input, but the output, you see, are associated with the edges. That means, what this means is that on receiving an input 1, the system moves from state P to state Q and generates an output 0. So 1/0 is 1 is the input, 0 is the output, and produces an output 0. So the output are associated with the edges. Inputs are anyway associated with the edges because on input you transition from one state to another. The outputs are also associated with the edges. Which in terms of circuit term means is that there is an output on you get an output instantaneously on receiving an input. At the same time, same moment, you get an output. Okay, the the important fact is that the outputs are associated with the edges, which means that output happens on input. Now the difference in the Moore machine is that the output, since the output is now not dependent on the input, it is only dependent on the state. You can associate the output with the nodes, with the vertices, not the edges. So this means, this diagrams means, the diagram B, it means is that you suppose you are initially in state P. On receiving an input 1, it moves to state Q and then gives an output 0. Okay, similarly, if you are in state Q, on receiving an input 0, the things associated with the edges are still the inputs. With receiving an input 0, it moves back to state P and then gives an output 0. So the output, as if, I mean, as if, of course, it will depend on the implementation. As if that you move to the next state. On receiving an input, you move to the next state, and in the next state, you produce an output. So the output is associated with the states, which are these circles, which are these nodes here, and the edges are associated only with the input, only with the input. Okay, so the only difference is that in the Mealy machine, the edges are labeled with outputs, whereas in the Moore machine, the vertices are labeled with the outputs. Okay, so that's the fundamental difference. That's the fundamental difference. Now let's see what. By the way, see in the this receiving an input. Usually, in a sequential machine, a synchronous system, what will happen that you will receive the input as well as the transition as well as the output. Everything happens at some edge of the clock, either the rising edge or the falling edge of the clock. So you get an input, you move to the next state, or you produce an output. Any of these three events can happen only in the edge of the clock. It's clock in a synchronous system. But in general, Moore machine and Mealy machine need not be just synchronous systems. They can be asynchronous as well. So it has nothing to do with synchronous or asynchronous. It's just what are the functions that determine the output and the next state. It depends on that. So it need not be synchronous. So in that case, this might make a difference, that when the output is associated with the edge, transition, or with the state. Okay, let's see what happens in the synchronous state, in the synchronous case. So let's look at this. I am kind of drawing not a state transition diagram, but basically a sequence of events that are happening. Okay, so imagine each of these columns as events, certain events, which in a synchronous case will happen at the clock, at the clock, or so rather let me state it like this. See, these columns which have this P, Q, and Q, these are like the gap between two edges of the clock. Whereas the columns where I have this 1 and an arrow and a 0, these are the edges of the clock where the transitions are happening. Let's look at like this. So let's say before this edge comes, so let me call this as just yes. Okay, let me try it here. This is something like this. Let's say I'm taking a leading edge. Then let's say it's like this, and then I am having a leading edge, and so on. This is my clock. Okay, so suppose before this let me call as edge 1, and this let me call as edge 2. Okay, so what happens in a milli machine is that, say before edge 1 comes, the system was in a state P. Now at edge 1, I receive an input 1. I receive an input 1. So here I was in P, here I was in state P. On receiving an input 1, I go to state Q. I go to state Q. I transition to state Q denoted by this arrow, and I produce an output of 1. I produce an output of 1 here. And let's say this is my state. So this was in P, and here it comes to Q. Okay, so now the system continues to be in state Q, still the next stage. The output continues to be in state 1, still the next stage. Sorry, the output was 0. Sorry, output was 0. Okay, so now the next stage comes, and then there is a transition back to Q. So it's back to Q again, the state is Q again, till the next stage maybe. And the output is 1. Output is 1 again. So now the output is 0. From here onwards, the output is 1. Sorry, it's 1. Okay, so this is what happens. So if we look at the output over the entire clock cycle, this one, it stays 0. And over the clock cycle, this one, it stays 1. Okay, so the input comes at, there is a transition at input. There is an output production also at the input. So everything, this production of the output moving to the next state, everything happens at this edge. So by the way, I'm talking this about a synchronous circuit. I mean, the similar description can also be given for the asynchronous circuit. Okay, now let's see what happens in a Moore machine. Let me also draw the clock here. Okay, so suppose the failed to align it anyway. This will, okay, forget about this. Let me try it here. Okay, so it was in a state P. The output was already, let's say, in output was 0. So this is state, this is output. This is the 0. Now at this rising edge, an input of 1 comes. Input of 1 comes. Okay. So what happens is that it moves to state Q. So this moves to state Q and produces an output of 0. So produces an output of 0. Okay, then it continues to be in a output of 0. Still the next input comes here, which is 1. Okay, which is 1. So you see the difference is that, so here the output in the milli machine, the output happens immediately when you get the input. Immediately when you get the input. But here so in terms of the synchronous system, it's actually the same. So here what happens, the first the input comes, immediately the output doesn't change. you first move to the next state Q and then produce an output 0. Okay, so there is this, it's not a full clock cycle delay, but there is, if your edge is kind of say some delta nanosecond or say epsilon nanosecond long, this edge, because edges are also not instantaneous in practice, there is a slight delay in the edges too. The edges also will take some time. So the difference between output being 0 here and the output being 0 here is this much, is a small delay. Okay, so the Moore machine displays the output a small delay after the Mealy machine displays the output. Or rather, putting it this way, whenever the input comes, the Mealy machine immediately displays the output, immediately produces the output, whereas the Moore machine will produce the output after a very small delay, which is as much as the delay of getting the edge, delay of transition from of the circuit. Whatever the circuit takes is a flip flop or something, everything will have a delay. Flip flop, when you give in a D flip flop, when you give an input, the same thing D is copied to Q, but with a small delay because of the latch. So that much delay will be there in a Moore machine in an implementation. In an implementation, in theoretically there is no delay. In the implementation there will be delay. Okay, so this is the almost same. But what we do is that for our analysis purpose, we ignore this delay. We say that the timing diagram of C and D, that is Mealy machine and Moore machine, are almost equivalent. We ignore this delay. Okay, so this is clear. Okay, anyway, forget about this delay thing. You'll really not be bothered about it for our all synthesis and design purpose. The takeaway is that you have the output associated with edges in a Mealy machine, and you have the output associated with the vertices in a Moore machine. That's it. Okay, so now let's try to design some Moore machines. Okay, so the problem is as follows. This is the first example. The example is as follows. You have to design a machine. Which takes as input a bit stream, single bit stream. Okay, takes as input a bit stream. Of course, it has a clock also, and produces an output which is 0 if it has seen an even number of zeros and odd. The output is 1 if it has already seen even number of zeros and odd number of ones. In all other cases, in the other cases, the output is 0. Okay, so let's look at like this. So first one, it has looked at 0 zeros and 1 ones. 0 zeros and 1 ones. So I'm assuming the bits are streaming in this direction. So first you get this, then you get this, then you get this, then you get this, then you get this. Okay, so first is 0 number of zeros and 1 number of ones. So output should be 1. Then you have these two. You have 1 number of 0 and 1 number of 1. So it does not satisfy the output. It should be 0. Then you get 2 zeros and 1 1. You get 1 again. Then you get 2 1 and 2 0. Then you get 0 again. Then you get 3 0 and 2 1. Then you get 0 again. Then you get 4 0 and 2 1. You get 0 again. Okay, I hope I'm correct. Okay, so this is what the output should be. So this is so-called the problem statement. So naturally, the input is it's a single bit stream. So the input is either 0 or 1, and the output is since it's an acceptor, it's kind of indicator. The output is also 0 or 1. So now we want to design a Moore machine for this problem. Okay, so how many states do we need? Anybody? How many states? What are the states that we should have? We are counting. We are basically doing a parity check on the number of zeros and a parity on the number of ones. Okay, so please tell me. Yeah, 4 states. What are the meaning of the states? What do the states represent?
Even, odd even, odd, and odd even.
Okay, so see, what we are doing is what we will do is that we will look at the last two bits, and so then depending on what this bit, or rather we'll look at the bits, and then all right. So let's look at the state. Let's say number of zeros and number of ones. So 4 possibilities are there. It can be odd and odd. It can be odd and even. It can be even and odd. It can be even and even. So at any point where you are counting the number of zeros and the number of ones in the bit stream, any of these, either any one of these 4 combinations can happen. So these are all that can happen. So these are the states. So let me denote them by Q0, Q1, Q2, Q3. Note that this is a symbolic representation of the states. I can as well have an encoding of the states. Okay, so so there are 4 states, 2 bits will be required. I might do an encoding like this. I can do a state encoding like this. Okay, so so these are the 4 possibilities that can happen. So at any moment of time, you can either have both even odd number of ones and zeros, odd number of ones, even number, odd number of zeros, even number of ones, and so on. These are the 4 possibilities that can happen at any time. Now, as every bit comes in, the number of parity of the number of zeros and number of ones will change by following the simple rules. I mean the obvious rules. So based on that, we draw the state transition diagram. We draw the state transition diagram. Okay. So state transition diagram is also very easy in this case. So suppose we start with even number of zeros. So initially, let's say the count is 0 for ones and 0 for zeros also. So you consider 0 to be even. So let's say initially you are in the EE state. Okay, now it's obvious. So now if you receive an 0, the count of zeros become odd now because you have 1 0. Count of 0 becomes odd. I'm talking about the output later. Let's first talk about the input. And if you are in even number of 0, even number of ones, if you receive one more 1, if your input bit is 1, then you still have even number of zeros, but you have odd number of ones. Similarly, let's see from here, if you have odd number of zeros and even number of ones, if you have received a 1, you have odd number of zeros still, and but you had even number of ones, now you have odd number of ones because you have received a 1. Okay, so this way it is easy to build this state transition diagram. Now our output, our delta was 0 and 1. So that means it's an acceptor for even zeros and odd ones. So you see that the output will be 1 only in this state. In this state, no, I mean in this state the output will be 1 because it is the acceptor condition, even number of zeros and odd number of ones. So you see the output is just a property. Output can be determined just by the property of the state, because we have defined the state in that way only. We have defined the state in that way only. So the output can be defined just in terms of the, note that we could have defined some other way of the states. We could have defined some other way. In that case, it might not be possible that the output depends only on the state. Output can be computed only from the properties of the state. It might not be the case. Maybe you could have less number of states, and then you have to take into account the input also. So in that case, it would be a millimachine. It need not be a Moore machine. But in this case, where you have taken 4 states, the output is directly a property of the state. So what we do is we associate the output values with the state. So we associate output of 0 to EE state, 0 to OE state, 0 to OO state, and 1 to EO state, and 1 to EO state. So this is clear. So this is why it turned out to be Moore machine. This you should clearly understand, because the way everything depends on it will be a Moore machine or millimachine depends on the relation between your state assignment and the output function. If you have defined your state assignment in such a way so that the output function is only a property of the state, then it is a Moore machine. If you have maybe done a different state assignment where you cannot define the output directly in terms of the state, present state, then it might not be a Moore machine. It might as well be a millimachine, because we need the input values also. Okay, but we in this case we have defined the states in a very straightforward way, so it's a Moore machine. Actually, often it turns out that if you use a millimachine where output is a property of the edges, you can often do with less number of states, often. And if you are using it with a Moore machine, you need more number of states, but the advantage is that you don't need extra logic to decide the output. It can be decided directly from the states. Okay, so this is clear to everybody. We have defined the states, and by the state transition diagram, the transition is on the input, and the output is a property of the state, so that so the output is associated with the states. Okay. Now let's draw the tabular form of this state transition diagram. So as before, let me repeat it again for those who have not yet followed. You have your set of present states, and on certain input, so each of these are one edge. So this is basically a transition from this to this state to this state, on receiving an input 0. This is a transition from this state to this state, E to EO, on receiving an input 1. So every edge in this state transition diagram is converted to one of these rows. In fact, this is actually 2 rows, on input 0 and input 1, one of these rows in this. So what this table basically means is that if your present state is EE, if you receive an input of 0, then your next bit is 0 in the stream, you move to a state OE. If your next bit in the stream is 1, you move to a state of EO. Okay, the important difference between the millimachine and Moore machine was that, if you remember, in the state transition table of the millimachine, we are writing the output here also. We are writing the output here also, 0 or 1. Okay, we are writing the output 1 here also. In the case of milli machine. Okay. But here you see the output is not dependent on the input. It's not dependent on I. It's dependent only on PS. It's not dependent, which basically means the value of the output is same for all the columns of input. For both the input columns, the output is the same for each row. Each row output is the same for both columns. Okay. Note that this would not have been the case in the milli machine. The milli machine, the output depends on the state as well as the input. So in the milli machine, it is possible to have 0 output in one column of input, 1 output in another column of input. But in Moore machine, that's not possible. The output is independent. It's don't care of I. It's not don't care. It's independent of I. For both I, the output will be same. It's a property only of the present state. If that be so, that its output is same, then I can remove this output from here. I can remove this output from here and write it as a separate column. Since it is, I can write it as a separate column because I need one column for one output for one state. It's not for all the inputs that are there in that state, that comes in for that state. For one row, I have one value. Every row, I have one value. I don't have one different value for every input. For all input, this states, this is the output. Okay, so that's the simplification. That's the simplification. So I can move it out. This basically means that okay. So now let's instead of the symbolic states, let's write the encoding for the state. So we have already chosen an encoding that 00 for E, 10 for OE, and so on. So I write down the encoding values. So this is EE, this is OE, this is EO, and so on. So I nicely have an state transition table. Okay, so now we want to realize this. So this is clear. Any doubt? Anybody has any doubt till now? I hope you will not have any doubt. Okay, so the only thing I want you to appreciate till now is that the state transition diagram as well as the state transition table are smaller or rather simpler for a Moore machine as compared to a milli machine. The trade-off is that a Moore machine, the equivalent Moore machine, might have more number of states. Okay, so if you are trying to realize this, actually, if you are trying to express the output as a Boolean function of the present state, it is, you can ignore the input. So it's a simpler circuit. Whereas in a milli machine, there would be 2 outputs in 2 of these columns, so it would be a more complex circuit. So basically, in Moore machine, you will have simpler logic circuits, simpler combinatorial circuit, but maybe more number of states. Whereas in a milli machine, you have more complex gate circuits, combinatorial circuits, combinational circuits, but you have less number of states. If they are equivalent, Okay. All right. So now let's try to write this as an truth table, or rather a Carnot map. Let's make a map like this. See, I'm just this table, this state transition table, I'm writing it as a Carnot map. So what I'm doing is as follows. I am writing I to be 0, and I to be 1, and I'm writing the present states. 0 0 0 0 1 0 0 1 and 1 1. This is my present state, and I am writing. Let me write the output. Let me write the output, or let me first write the output function. Okay, so let me copy. If the so what will we see? See, it is dependent only on the. So this is, let's see the on bit, on combinations, on rows of the output. So it is on only for the present state to be 1 0. So present state to be 1 0. This is 1. This is for all inputs, so both of these should be 1. This is the Karnaugh map. Okay, so if I represent the present state by two variables, let's say x and y, so this is x and y. So can anybody tell me what is the output O as a function of x and y? What is the Boolean function f? Anybody please tell me. What is the Boolean function? I'll come back to the I'll come back to the circuit for doing the next state, for determining the next state from the present state, because that will require memory, that will require flip-flop. I'm explaining that. But this is just combinatorial circuit. So can you just tell what is f from this
XY conjugate.
Yes. So O is XY conjugate, as simple as that. You see, this makes sense because I am, what is my indicator, what is my acceptor functions? It is, my states are E. E means 0 0. So I am checking, basically I am checking for 1 0. Or I'm checking for 1 0. So odd number of zeros and even number of ones. So it is XY bar. That's the simple definition. Okay, now let us see the transition function. Let us see what is the implementation of the transition function. So let's try to remember the Huffman model. So let me quickly tell what it is. So you have an input which is a bit string, say 0 0 1 1 0. We have an input bit string. We have an output which will be 1 for what is the acceptor? Even 0, odd ones. Which will be even 0, odd 1 is the acceptor, 0 otherwise. This is Z. And then you have a present state which is Y. Let's denote by capital Y. So this is my primary input. And your present state, I'll come back to that. Let me call this as present state, is my secondary input to this combinational circuit. Okay, so now you see, to get the next state from the present state, you need some memory elements, basically flip-flops. You need some memory element. So these memory elements, in this case, a state is represented, the encoding of the state is 2-bit. So basically he will need here 2 flip-flops. This memory element will be consisting of 2 flip-flops. What the flip-flops will do, they will take the present state. They will take the present state, which is actually 2 lines. The present states, because the encoding has 2 bits, so it is X and Y. Okay, maybe I'm getting messy with the symbols, but okay, it's the two states, say even, odd, or odd even, or something like that. This is two states as input and two states at output, which is the next state, which may be O, E, and so on. So you need two flip-flops, and of course you need a clock. So what this memory element does is that if at current clock it receives this Y, sorry, I think I'm making a mistake. It's not actually, this is not actually new state. This is the state which is held for some time, which is memorized for some time. Okay, so the moment you have a new state, say you are in the logic says that now you should move to EO state. What it does is that this memory element, suppose I have EO as input, this will hold this, and this will be whatever it holds in the next, for till the next clock cycle, till the next transition in the general case. And in the next transition, it will use this EO value. It will use this EO value to compute the Z as well as the new state. Let's say the new state is OE. It will use it to compute this. Okay. So so these are called memory elements because they are holding it till the next transition. Whatever value you want to be, they are holding it till the next transition, till the next transition is computed. So a current transition is computed, till the next input comes, till the next transition is computed, it will hold on to that value. It will memorize that value. Okay, and we will need two flip-flop to do it in our case. Now, you see these memory elements will be flip-flops. They can be a simplest case, the D flip-flop. They can be as well SR flip-flop, JK flip-flop. Depending on what type of latch you use, it can be different type of flip-flops. Now, you know the mechanism by which in a D flip-flop in which you give an input and it is held till the next clock. It's held till the next clock is very simple. You give an input, the same value in the D flip-flop is held. But in other flip-flops, it's not so simple. For example, you can have an SR flip-flop. Okay, so what value is held depend on the combination of this S and R and so on. It depends on the combination of S and R. So, you know, suppose your present state is OE, I want to hold that value till the next transition. What it's not in D flip-flop easy. You set the D to those values, they will be held. But in other flip-flops, for example, SR and other, it's not direct. You have to set, depending on the logic of those flip-flops, you have to set the values of S and R or J and K so that the desired value, the desired state is held to the next state. Okay, so this function, whatever input comes here and the values held here, so input in the sense what are the values of SR and then what are the values of Q, this is called an excitation function of the flip-flop. It's called an excitation function of the flip-flop. Okay, so this will also determine your logic because to hold this value, you have to actually determine the proper value of Y depending on your excitation function so that the desired value of Y is held till the next transition. So the values you generate here need not be direct state encodings. They have to be some inputs such that the output is held to the desired state encoding, the next state encoding. Or rather in this case, I mean, in our terminology, this is the present state encoding. Okay, in D flip-flop, this excitation function is an identity. Whatever is input goes to the output. We'll see in other flip-flop that this might not be the case. So what this basically means is that we need some more circuits here so that the desired, not just the state, you get the state here and you need some circuit, maybe the state to the SR values, you need some circuit to convert it. Okay, but overall the principle is same. You have memory elements, you have a combinatorial combinational cloud, which will convert the input and the present state to the next state. In the case of Moore machine, this actually looks like this. If you expand it a bit further, so this what I'm doing here is basically expanding this combinational cloud. Okay, so the combinational cloud consists of the following two different blocks. One block is the transition logic, which takes the input, takes the current state, and produces the next state. So this is the transition logic, basically a gate circuit. And then the state memory is this flip-flops, is the state memory. And the state memory, what will do is that it will hold the present state till the next transition. Hold the present state till the next transition. And then of course, you have an output logic. In the Moore machine, the output is determined only by the present state. So this output logic will take as input the present state S and produce the output. In case of Mealy machine, this could have also gone here. This would have also gone here. Okay, so let us try this. So can you this transition table, can you tell me a D flip-flop realization of this? So I should have copied this transition table, but let me see. Let me see if I can. Or oh, I already have it. Sorry. Okay, so let's look at like this. So I have two D flip-flops. I'll need two D flip-flops. I'm not drawing the Huffman model as such. Let me draw it, or let me draw it like the Huffman model. So I have two flip-flops. I have D1 for the first flip-flop and D2 for the next flip-flop, and I have Q1 and Q2. I'll ask you to draw two circuits. One is, and then I have an input, only one input I. The first circuit will take Q1 and Q2 and I. So it will have I, Q1, Q2, and produce D1 and D2, which will feed back here. And the next circuit will take as input Q2 and Q1 and produce output. Let's call it O. So this circuit we have already made. It is XY bar. Rather, it is Q1, Q2 bar. This circuit we have already made. Okay. I'm drawing it in a worst possible way. But now let us try to build this circuit. Can you draw all of you, can you please draw the Carnot map for this circuit? So it takes as input I, Q2, Q1. It's a 3 variable Carnot map, I, Q2, Q1, and two output, D1 and D2. So there will be two Carnot maps, one for D1 computed from I, Q1, Q2, and one for D2 computed from Q1, Q2, I. Can you quickly draw these two Carnot maps? I have already given you the table. So from the table you can do there will be two Carnot maps, each of these three variables. This is for D1. Let's say I have another kernel map for D2. Okay. So can you please tell me what is this kernel map, sir? Anybody of you, please fill up this kernel. Tell me the on a cells of this kernel map. On min terms, please. For D1, what are the on min terms? You can tell it from this state transition table. Okay, you can tell it from the state transition table. So this is my input, this is my PS, and these are my new state. Let me call it new state 1 and new state 2, the 2 bits of the new state, and these are my PS. So this is PS1 and this is PS2, the 2 bits of the PS. Okay, now fill up this kernel map. Tell me what are the on entries. Anybody for D1? What are the on entries for D1? Please. Yeah, I'm on. What are the on entries for D1? Complete this kernel map for D1. Anybody, please tell me the on entries for D1. Okay, so let's look at this column. Let's look at this column. So what will be the on entries for this?
Sir, the second and third row PS are same. Students say.
Second and third row of D1. Oh, second and
PS
third row are
doesn't
same.
say.
Sorry, I made a mistake. Yeah, second and third row are same. So let's correct it. So let's go back to this. So this will be, wait.
Sir, third row should be 0, 1.
Third row should be 0, 1. Third row should be 0, 1. Yeah, EO is third row 0, 1. And are these correct? Yeah, these are correct. The new states are correct. New states are correct. Very good. So now you tell me. Suppose I replace it by 0, 1. This is wrong. You replace it by 0, 1. So what are the on entries in the kernel map? So the kernel map, the first row of the kernel map. Let's take the first row of the kernel map. I equal to 0. All right. So you have 1 at 3 places. 0, 0, 0, 0, 0, 0, 1, and 1, 1. 0, 0, 0, 1, and 1, 1. So the first column, third column, and fourth column will be on. You look at the first bit of I equal to 0. So I equal to 0 is the first row of the kernel map, and D1 is the first row of the I bit. So it is 1 at 3 places. 0, 0 for PS1, PS2. 0, 1, I made a mistake here, 0, 1, and 1, 1. What about for I equal to 1? When are the first bit 1? Again 3 places. At 0, 0, 1 0 and 1 1. So can you give me the logic function for this Carnot map, the minimized logic function for this Carnot map? See, what I'm doing is as follows. What I'm doing is as follows. What is this? Yes. So see, this is D1. So this is the first bit of new state. And I equal to 0. So this is this row. I'm looking at the 1. The 1 is at 0 0. This will be 0 1. The 1 is at 0 1. And there is a 1 at 1 1.
Excuse me, sir.
Yeah.
So the last element of the highlighted column should be 0 1. So the I equals to 0
row.
column. So
The
last row,
this should be
second
0 1.
Yes, sir.
Okay. So then I don't have this. Then I have this. Good. Okay. So I equal to 1. Is this correct? So I have a 1
Yes,
here.
sir.
I have a, yeah, good. I have a 1 here. I have a 1 here. And I have a 1 here. Okay. So what is the logic circuit? So maybe the only minimization that I can, there are two minimizations that I can do, this and this and this and this. So what is the logic? What is D1 as a function of I, Q1, Q2? What is this logic? Can you quickly tell me? So it is, let's see, it is Q1 bar, Q2 bar for this. And this is, yeah, this is, what is this one? What is the min term for this? Tell me, what is the min term for this? What is the problem with? I think I made a mistake in this Carnot map.
Sir, they are not adjacent elements.
Yeah, I have made a mistake. Okay.
So also in the I equals to 1 column, the first element will be 0 1.
It will be 0 1. Yes. It will be 0 1. So in this, so let's try to fill up this one. If we try to fill up this one, 0 0 for I equal to 1, second is 1. Sorry, this is 1. And then it is 1 for 1 0. 1 0, it is 1. And then it is 1 for 1 1. For 1 1. So is this correct? I have to go back to track this, but I believe you. So of course you are correct. So yeah, I think this is fine. Let me check. So it's,
Sir, in K-map, the third column should be 1, 1, and the fourth column should be 1, 0.
yeah, I made that mistake again. Okay, so let's draw the correct one. Okay, so this, what are the corrections here? This becomes 0, 1, and this becomes also 0, 1. Just check this if there are any more errors. Check this if there are any more errors. No, I think these are correct now. So odd, then I have a 0, so it's even odd. Okay, I think these are correct. Okay, so now let's do it. So it's the first row. Let's look at the first row. So it's 1 here, and a 1 at 0, 1, and a 1 at 1, 1. No, 1 at 1, 0, 0, and 1 at 1, 1. 1 at 0, 0, and 1 at 1, 1. Next, I equal to 1. It's 1 at 1, 0, and 1, 1. 1, 0, and 1, 1. So this is the kernel map. So the only minimization you can do is this. So you can write your D1 as, what you can write? You can write it as present state 1, present state 2 for this. What is this for this? Plus it's present state 1 dot I plus, what is this? It is PS1 bar, PS2 bar, I bar. Okay, so this is what goes as, so this circuit will be this. So what is this? There will be, it's a AND-OR representation. So you can draw the AND-OR representation. I don't have space to draw it here. So this is the AND-OR representation for D1. Similarly, you can do it for D2. Okay, so you have got the procedure. You got the procedure. So actually what you have to do basically is that you have to draw the state transition table, and for different combination of PS, the state encoding and the input, you have to look at all the next state encodings, every bit of the next state encoding, and for every bit of the next state encoding you have a separate circuit which you draw a kernel map and find out the circuit. That's it. So this is simple. I mean, I'm not dwelling more on this because I hope this is very easy for all of you. You just have to be careful that you are doing all this correct. You are just tabulating everything correctly. That's what needs to be done. Okay. Now let's look at the next problem. The problem is as follows. You have a stream X coming in of zeros and ones. Okay, and you are having it from the MSB side. So if you think of the stream, so first one comes, then two comes, then one comes, then zero comes, zero comes. Then actually it's a number. Let me call it n, which is 11100. This is the number. So from MSB first, the bits are streaming in. MSB first, you are reading in the string. And as you get these numbers, you have to find out the remainder. Remainder on, if we divide n by 3. So your output can be 0, 1 and 2. You have the output 2-bit output encoding of 0, 1 and 2. So you read in the number MSB first, and then in the output you have to print the remainder, which is either 0, 0 or 0, 1 or 1, 0, because it is division by 3. Okay, and I have to design a Moore machine for this. Okay, so can you tell us tell me a state assignment, a good state assignment for this? Tell me a good state assignment for this.
The state for each of the remainders.
One state for each of the remainder. Yeah, naturally in Moore machine actually it's very simple, since not exactly very simple, but okay, often it is very simple. So you have states for 0, 0, 0, 1 and 1, 0. And how do you get the transitions as you get the input? What happens if your next MSB is 0? What happens to the state? So suppose you have read in these 2 bits. What is the remainder of 1, 1? Which state are you in?
0.
0, 0. And if the next bit is 1, what is the remainder?
1.
So there is a transition like this. If the next bit is 0, so currently you are in this state. What is the transition?
So from 1 to 2.
A transition like this. Okay, so depending on what your next input is, you get your remainder changes. So let's see the thing. So let us represent 3 states. Symbolically, the encoding is 0, 0, 0, 1, 1, 0. But symbolically, let me represent them as R0, R1, and R2. Symbolically, I am representing them. Now, let's see the rules. If my remainder is 0, and okay, in a Moore machine, you associate the output with the state. So naturally, if the remainder is 0, output is 0. Remainder is 1, output is 0, 1. Remainder is 2, output is 1, 0. Now let us look at the transitions. Let us look at the transitions. If your remainder is 0 and your next bit is 0, you have a trailing 0. The remainder stays 0. If you already have remainder to be 0 and you get a trailing 0, remainder is still 0. If your remainder is 0, as you have said, if you get a 1 next, you get a trailing 1 next, your remainder becomes 1. Because you are adding a 1. So whatever it is, some number of bits, you are adding a 1, your remainder also will get added by 1. Can you tell me, anybody, why this happens? If you look at the formula for binary representation, why this happens actually? Anybody, just a quick one-line explanation. Quick one-line explanation why this happens. So see, this is the current input that we are reading in the number so far. It's the least significant bit. It's the least significant bit. Okay, so you either get 1 added to it, if it is 1, or 0 added to it. If you have 1 added to it, naturally the remainder will increase by 1. It's modulo 3 division. If you have 0 added to it, the thing says the same. Okay, so that's why you have this transition. And as you have said, if your remainder is already 1, if you have another 0, your remainder will now become 2. Okay, your remainder will now become 2. You have a trailing 0. Your remainder is 1. You have one more bit added in, so these bits, your x will actually be multiplied by 2. Okay, you are shifting the bits to the left, so they will be multiplied by 2. They will be multiplied by 2 and a 0 will be added. So remainder will now become 2. You are shifting to the left. One more bit trailing 0 comes in means that you are shifting it to the left. Here the trailing 0 does not create an effect because anyway there are leading zeros also in R0. Okay, similarly if your remainder is 2, see every time a new bit comes in, you see there is a left shift. Every time a new bit comes in, there is a left shift. And left shift means you are multiplying by 2. Okay, and then you are adding one more LSB. Depending on that LSB is 0 or 1, your remainder will be changing. It will be incremented. It will be incremented. So there will be a change due to shift, and there will be a change due to increment due to the LSB coming in. Okay, so I guess this diagram now will be clear. So if your remainder is 0, you get 1, you get a remainder of 1. Left shift is there, but since it is all 0, it doesn't double really. And then you have R1, then it doubles, and then you add 1. So you get a remainder of 2. If it doubles and you still get another 1 coming in, then your remainder is back to 0, 0. You have 1 and it is doubled, and then one more comes in, it's back to 0. So R1 goes back to R0. Similarly, R2, one more 0 comes in, it's doubled, and then one more 0 comes in, it goes back to R1. Okay. All right. Any question? All right. So then now we have R2, then again once comes in, it's shifted, and then 1 comes in, so it stays 2. So this is the diagram. So I have written it down in a tabular form. It's very easy actually. So I have written it down. So your job now, all of you quickly take your pen and paper and find out the D flip-flop realization. I'm keeping this diagram in the screen. You quickly first draw the Carnot maps. So you need to, you have 3 states. You have 3 states, so you'll need 2 flip-flops to store them. You'll need 2 flip-flops. Note one thing, that one more interesting thing happens here is that you have, so one of the state doesn't appear. So in the transition logic, you will have some don't cares. You will have some don't cares because one of the row will be missing. You don't have 4 rows here, you have 3 rows here. One of the row is missing. So there will be some don't cares. So corresponding to this, suppose I am using 2 flip-flops, 2 D flip-flops to encode, to store these 3 states. You quickly give me the Carnot diagram for O and NS1 and NS2. Every state will be 2 bits, so NS1, NS2. I will be 1 bit, O will be 2 bit. So you give me the Carnot map. So there will be 4 Carnot map, NS1, NS2, O1, O2. All of you please draw and upload in your chat. Please draw and upload in the chat. I'm keeping this in the screen for your benefit. It's a almost a trivial exercise, but this will help you remember things. all of you, please please upload in the chat. You draw the 4 Carnot maps. They are simple. It will not take much time. First, copy this transition table and the diagram. Then maybe you can. It will be easy to make. Let's see if anybody has done. Okay, so Satvik, this is for. Can you draw? Just you type in. You see there are 2 rows. You just type the rows line by line. Say, let me see for the K map for O. Can you type the K map for O in this format? Say, for example, 0 1 0 1 is I equal to 0. 0 1 1 0 is for I equal to 1. This way, in this case, it will be more. It will be S1 and S2. Can you quickly type the Carnot map here? Anybody of you, can you quickly type the Carnot map here in the chat box? You need to make 3 Carnot map. One for NS1, one for NS2, one for O. Oh, O also you need 2 Carnot map actually, O1 and O2. So 4 Carnot maps. So NS1 Carnot map, anybody? Anybody just type in the chat box the Carnot map for NS1. You will need only 2 rows, each with 4 entries. Can you type it?
Sir, can you please show the question again? Actually,
yeah. Can you see?
Yes. Just give me.
So let me explain once again also. Let me explain one again. So you have 3 states: 0 0 0 1 1 0 encodings. These are the present state. These are the next state. So what I want you is to draw a Carnot map for this first bit here, the second bit here, first bit of O, second bit of O, first bit of NS, second bit of NS, first bit of O, second bit of O. I'm keeping this here. For each of the, you just write down, for example, NS1, then you type 2 rows. Karnaugh map for NS1. Similarly, NS2, you type 2 rows for the Karnaugh map of NS2, O1, O2. So these 4 Karnaugh map, you just type in the chat box. It should be very easy. But just I'm forcing you to do this exercise because I hope that once you do it, you will not forget it. All of you, please do. All of you, those who can do it's fine. It's fine. I know they can do, but this is a common denominator. Everybody should be able to do it. So everybody, please do it. Okay, just copy this diagram or table or diagram, whatever. Both of them can be used, and then I'll move from this screen. Note that there will be some don't cares because I don't have 4 meaning. I have only 3 states which I care about. So the 4th state is really not very important. So there will be some don't care in the Karnaugh maps. The input combination 1-1. Input combination 1-1 for PS1 and PS2. That's a don't care. So one of the column will be a don't care. Yeah, correct. So NS2 is 0, 0, don't care 1, and 1, 0, don't care 1. Correct. Satvik also correct. Very good. Yeah, Yasika, you have written. Yeah, excellent. Good. Rian, nice. Ravinder Sai, what is the meaning of this? Oh, okay, okay, good, got it, got it. You have three Karnaugh maps side by side. Abhishek, got it. So very good. I'm happy that you are doing it. So now the anybody, just one of you, I'll not waste much time. Any one of you, can you give me the Boolean function for, let's say, NS2? Anybody, can you give me the Boolean function for NS2? Anybody can give the Boolean function for NS2? Yes, good. Good. So Rithavan, it's what is x? X is PS1, I guess. PS1 and y is PS2. Then x plus y prime. Nice. Yeah, good. Very good area. I prime Q1 plus I Q1 prime Q2 prime. Yeah, good. Excellent. Nice, nice. Thank you. So yeah, you are not as stupid as me. I would have surely be making mistake in this, but good. Yeah, good. So now let us move to the next problem. Thank you. I think I guess all of you can do it now. All right. So now let's come to a little bit more complicated thing. Now we are still computing division modulo 3. So your output, so input is again a binary string, single binary bit stream. output is still the remainder, which is 0, 0, 0, 1 or 1, 0. But now instead of from MSB side, I have the bits coming in from the LSB side. Okay, so if you have the LSB bit first, then the zero position, 0 index bit first, then the 1 index bit, then the 2 index bit, and so on. Okay, and now if you want to find out the modulo division remainder, it's slightly more complicated, because you not only have to remember the see earlier in this case you just have to remember what the current remainder is. If you just remember what the current remainder is, depending on what your next bit is, next less significant bit is, you can easily find out what the next remainder will be. But now the next remainder will not only depend on the current remainder, but also the next bit that you are giving is coming at an odd index or an even index. It's coming at an odd index or an even index. So currently you have seen odd number of bits, odd number of values, or even number of values. So accordingly, the next index is 1 or bit. So the rule is as follows. Initially, let us assume remainder to be 0. Okay, and then you get an, if your next index is even, note that we are reading it from the right to left. You are reading the LSB, then you are reading the 0 index, 2 to the power 0, 2 to the power 1, 2 to the power 2, that order. You are reading in that order. So if you get a 1 on an even index, the remainder 1 gets added to the remainder, current remainder. Okay. Whereas if you get a 1 in the odd index, 2 gets added to the current remainder. Okay. Also, you need to so basically you need to keep track whether the next bit that you are reading, the next value that you are reading, the index of that is of even parity or odd parity. The next index is even or odd. That you need to remember. Okay, so now, so earlier I was only remembering what the current remainder is. It can be 0 or 1 or 2. Now I need to so this rule you can easily check out. You just check any example. In fact, if you write down the expression for a Boolean number of a binary number, you can easily check this fact. You can easily check this fact. Okay, so now I need to remember not only the current remainder, but also the next input that will be coming, the index position of that next input. It is an even numbered index or an odd numbered index. I need to remember these two. So naturally, I'll need 6 states. First state is that the next index is even and the current remainder is 0. The next index is even and the current remainder is 1. Next index is even, current remainder is 2. Next index is odd and the current remainder is 0. The current remainder, I'm calling it as an accumulated remainder so far. Next index is odd, current remainder is 1, and so on. And these are the encodings for that. These are the encoding for that. Okay, so this rule you can easily check. You check any number. And check the remainder from the LSB side. So now you are whenever a new number is coming in, you are actually doing a right shift, not a left shift. You are doing a right shift. And right shift is more complex. Depends on the shift is on an even bit, even index, or an odd index. Okay, so you can easily check this. I'm leaving it to you. You just take the formula for a binary number, 2 to the power 0, 2 to the power 1, and the bit values. You can easily check this. Okay, so any of you, can you and this encoding, see in this rule, the only thing I need, there are 2 things I need to remember: the current accumulated remainder, which is 0 or 1 or 2, and the position of the next bit, index of the next bit, which is again even or odd. So I have 6 combinations. Okay, so now you tell me the transition diagrams. All of you first attempt the transition diagram. Suppose the next bit is even. Currently I have a remainder of 0 and the next bit is even. Next bit position is even and I get an 1. So if my current state is E0 and my input is 1, what will be my next step? Can anybody tell? From E0, according to this rule, if my index is 1, what will be the next step? What will be the transition? Anybody? E0 on input 1 transitions to which state?
0,
Anybody?
1. O, sorry.
O1. It transitions to O1. It's all written down in this rule. Similarly, E1, E0 on input 0, what state it transitions to? E0 on input 0. Just this is not written down here, but can you tell me what the rule?
O0.
O0. Very good. Similarly, E1 on E1 on input 1. E1 on input 1. This is given in this rule. E1 on input 1. It will move to E2. Oh, sorry, it will move to O2. It will move to O2. Right. Okay, so let me draw the transition diagram. Let me draw the transition diagram. So this is what we have said. E0 on input 1 moves to O1. E0 on input 0 moves to O0. E1 on input 1 moves to O2. E1. So this is the rule. You see that on input 1 gets added. 1 gets added. But it becomes O because the next, if the current position is even, the next position will be O. So see there is no transition from any E to any E naturally, because if the current position is even, next position. Similarly, there is no transition from any O to any O. It's all from E to O and O to E. And E to O, you see the 1 transitions on input 1 transitions are to the next level. So E0 moves to O1, E1 moves to O2. E1 moves to O2. Okay, on the and there is a wraparound. So E2 moves back to O0. E2 moves back to O0. What are the transitions on 0? You see from the even, transitions on 0 are to the same level. So E0 moves to O0, E1 moves to O1, E2 moves to O2. And similarly back. So O2 moves back to E2, O1 moves back to, on 0, they are just back. O1 moves back to E1, O0 moves back to E0. Okay, but O0 on an, see there is, this is a, so E2, so E0 moves to O1, E1 moves to O2, E2 moves back to O0. Similarly, O0 on 1 moves back to E2, O1 on 1 moves back to E0, O2 on 1 moves back to E1. So O2 goes to E1. So for E, you see it's forward, E to O1, E0 to O1, E1 to O2, E2 to back to O0. For the O, it's the reverse. So O2 goes to E1, 1 goes to E0, and O0 goes back to E2. Okay, O0 goes back to E2, and the output is easy. Output is easy because this is its remainder is 0 in E0. Remainder is 0 in O0 as well. Remainder is 1 in E1. Remainder is 1 in O1 as well. Remainder is 2 in E2. Remainder is 2 in O2 as well. So the output is associated with state. It's easily computed from the states. Okay, so yeah, you draw the state transition table for this. Just draw the state transition table. So how many rows will be there in the state transition table? There are 6 states, there will be 6 rows. But you see that there will be 6 rows. But if you look at the encoding, since there are 6 states, you will need 3 bits. So there will be two rows which are missing from the state transition table. So accordingly, some don't cares will come in the kernel maps. Some don't care will be coming in the kernel map. So and the output there are see how many flip-flops we'll need to store to realize this. How many, let's say, D flip-flops will be required to realize this? Anybody?
3.
3 with D flip-flops.
3.
So if we label them as D1, D2, D3, and you have only one input I, so it will be a 4 variable kernel map. And how many such kernel maps do we need to draw for computing the next state as well as the output? How many kernel maps we need to draw total? So it will be a 4 variable kernel map, 3 variable for the states and 1 variable for the input. D1, D2, D3 and I. It will be, everything will be a 4 variable kernel map. And how many such kernel maps we will need to complete this?
4.
4. No, 4, not 4.
5.
5. So there the next state encoding is 3 bit. So for each bit of the next state, we will need a kernel map. So 3 kernel maps for the next state computation, and the output is 2 bit. So you'll need 2 kernel map for each of the 2 bits of the output. So there will be 5 kernel maps in total. Each kernel map will be a 4 variable kernel map, 3 for the state encoding and 1 for the input. It is a 3-bit state encoding. Okay, so well, I am not attempting to draw 5 kernel maps here, but you can easily draw it, and you can easily find out the Boolean function and realize that. Okay, but as a ending note, what I would say that if you tried to realize this same thing using a milli machine, you will actually see that you can do it less number of steps. Of course, the logic will be difficult, more complex. You can do it less number of steps. So what we'll do in the next class is that we'll see these are 2 representations of a FSM, a Moore machine and a milli machine. We'll see both of them have the same expressive power. Whatever FSM can be expressed as a Moore machine can also be expressed as a milli machine and vice versa, which means that any Moore machine can be converted to a milli machine and any milli machine can be converted to a Moore machine. So in the, of course, the number of states and all those things will be different. The logic will also be different, but they can be converted. So in the next class, we will see how the procedure for converting a Moore machine to a milli machine and a milli machine to a Moore machine. Okay, so thank you for today. Okay, so all this I am not doing, but I suggest that it will be a good exercise for you. Okay, so I'm stopping for today. Some more announcements I would like to make. Some more announcement I would like to make. First of all, is that